got this region enclosed by r equals cos theta and r equals sine 2 theta. Shown in the book, let's go ahead and have the calculator graph this as well. R equals cos theta and r equals 2 sine 2 theta are two different polar curves. If you want to graph it in your calculator, in your mode screen, you'd want to make sure you're in polar mode. If you're in polar mode, then you can graph them both as functions of theta. And looking at the picture in the book, it seems like maybe theta just goes from 0 to pi over 2. In your window screen, I'm going to go from not 0 to 2 pi, but I'll go to 0 to pi over 2. And I will look at the picture just in the first quadrant. So I'll pick positive values of x and y here. I think we only need to go out to maybe a little bit past 1. I'll go 1.5. Make these 0.5 apart. Graph it. Well, it almost made them like it was one curve, but it's two distinct curves. You should be able to think about, without actually plotting points, you should be able to think about which curve is which. Cosine of theta when theta is 0 is 1. So r is 1 when theta is 0. You're one unit of distance from the origin when theta is 0. It's got to be this curve. That's not the ordinary graph of the cosine function, right? It's a polar graph. It's a different kind of graph. It looks more like the sine, actually. Not the sine either, but it's the cosine function in polar coordinates, where you graph points where r is determined by this equation. So you let theta vary, let the angle vary, and graph along radial lines emanating from the origin, a distance of r. Until we get to r equals 0, which is going to happen when theta reaches pi over 2, 90 degrees. But the other one's got to be sine 2 theta. Yes, sine of 0 is 0, so we start at the origin. We reach a maximum when what? When the sine of 2 theta is 1. We're 1 unit from the origin right there. At about a point with coordinates 0.7, 0.7. That's going to happen when the input for the sine is pi over 2, which means 2 times it is pi over 2, which means the angle itself is pi over 4, 45 degrees. And then we're back to 0 once we reach pi over 2, because we get sine of 2 times pi over 2. Sine of pi is back to 0. We're interested in the area between these graphs. Draw by hand here. First graph looking like this. Second graph looking like this. That's r equals cos theta. This is r equals sine 2 theta. And the area we're interested in is that. That's an area swept out, but really by two distinct polar curves. You need to imagine drawing a line in here like that, distinguishing the lower half, which is swept out by sine 2 theta, from the upper half, which is swept out by the other curve, cos theta. As the angle varies, area is getting swept out. It's tricky. You have to think of it in the right way. What is this angle right here? It would be the angle where these are equal to each other. So you also have to solve the algebra equation, cos theta equals sine 2 theta for theta. And trig identities are really useful in solving trig equations. Maybe you never had a class that had enough trigonometry, or maybe you did and you just forgot. But sine 2 theta, there's a double angle formula that you can look up that says sine 2 theta always equals 2 sine theta times cos theta. Always. It's an identity. It's not an equation to solve for theta. It's always true. That's an equation to solve for theta. It's not always true. So these equal signs actually mean different things here. That's an equation that's always true. That's an equation that's only sometimes true. We're trying to figure out ultimately what values of theta make it true by figuring out what values of theta make this true. Now it's tempting to cancel the cosine of theta here right away, get rid of the cosine. And that technically does work here because the angle is in the first quadrant. But in general, you'd want to, instead of dividing both sides by cosine theta, you'd want to rearrange and have cosine theta on one side factored out like this, and 0 on the other side. You technically should do it that way to be a bit more rigorous and include all possible solutions. This means in order for this product to be 0, either cos theta is 0 or 1 minus 2 sine theta is 0, which of course is equivalent to sine theta is a half. There's infinitely many solutions to both of those equations. The solutions of this equation are theta equals pi over 2, and any integer multiples of pi over 2 added to this. 3 pi over 2, 5 pi over 2. Actually, yeah, that's right. Etc. Negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, etc. And this equation is true when theta is the inverse sine of a half, which turns out to be in degrees, 30 degrees, pi over 6. Any multiples of 2 pi added to that. 2 pi is 12 pi over 6, so that would also include 13 pi over 6, 25 pi over 6, etc. It also happens to be true at negative angles, negative pi over 6, negative 13 pi over 6, negative 25 pi over 6, etc. But of all these infinitely many answers, we only need one of them, pi over 6. That's the one that's drawn. Pi over 6 there, 30 degrees. So the integral for the lower area swept out by the upper curve, so to speak, right? R equals sine 2 theta is this curve right here. That's the upper curve, so to speak, up here, but it's the lower curve down here, but it's sweeping out this area as the angle varies. That's the first integral from 0 to pi over 6. And then the second integral would be from pi over 6 to pi over 2 of the other graph, which would be this one. The area, the formula for area is 1/2 times the integral of the function squared. So the lower one again, oops, I almost made a mistake. Rewrite that. I mean, I'm going to add these integrals anyway, so it doesn't really matter. But the lower curve here, which is sweeping out this lower area, is again sine 2 theta. So that's got to get squared. I'll write it as sine squared 2 theta. As theta goes from 0 to pi over 6, time plus 1/2 times the integral of the other one from pi over 6 to pi over 2. And that other one was cos theta, and it gets squared. I'm using the formula 1/2 integral from alpha to beta f of theta squared. That's what I'm using there. That's why you see these functions being squared and having the 1/2 in front. To do these by hand, use more trig identities. Replace cos squared theta with 1/2 plus 1/2 cos 2 theta. That is a trig identity. Those are always equal. Does it have a name? I'm not sure if it has a name, but I always remember it because I always teach it in Calc 2. If this were a sine squared theta, by the way, instead of a cos squared, that would just be a minus sign there. That's the only difference. It's still a cosine there. Cos squared theta is 1/2 plus 1/2 cos 2 theta. Sine squared theta is 1/2 minus 1/2 cos 2 theta. Once you make this replacement, it's easy to integrate, right? 1/2 is easy to integrate. That's easy to integrate. You can do it in your head. Similar kind of thing with this one, although it's a little trickier because, well, it's a sine instead of a cosine, and it's a 2 theta in there instead of a theta. That would be 1/2 minus 1/2 cos 4 theta. Do the same kind of thing you did over here, but replace the thetas with 2 thetas to get a 4 theta there. Once again, once you've done that, then the integrals relatively easy to do. So I won't finish it by hand here, but that's what you would do to finish it by hand. That's the start. And then we'll get the answer with Mathematica. Let's just do each integral individually as well. So the first integral, 1/2 integral from 0 to pi over 6. I'm going to type it in Mathematica. I should probably put the square on the outside. Kind of a complicated number, but there it is. And then for the other one, 1/2 times the integral from pi over 6 to pi over 2. To get exact values, you'll also need to remember exact values of sine and cosine. Cos theta squared. Still kind of complicated. Add those two things. I can do that like this. Percent sign refers to the preceding output. Double percent sign refers to two preceding outputs. Simplify. Okay. There's the answer in exact form for the area. That's approximately about 0.23 is the area. By the way, if you want to graph them in Mathematica, it's polar plot. Cos theta and sine 2 theta. Let's graphing them both. Then we're getting this area. So there again is the answer. So when you do finish it by hand, if you haven't yet, hopefully get that answer. How is this related to double intervals? Well, suppose we were trying to integrate, find the area of this region another way. Same region, right there. Trying to figure out the area of that another way. How about as a double integral of the constant function 1, right? We know double integral of 1 gives you the area of the region. Mentioned this a couple weeks ago because it's the same as the volume under the graph, but a constant function of 1 has a height of 1. Technically, the units of the area and the volume are different. Cubic inches, for example, for the volume versus square inches for the area. But because it's a cylinder, so to speak, of constant height above your planar region, the double integral for the volume gives you the same numerical answer as the area of the region. So we'd have to do a double integral over this region. Let's call this region D for domain. I'll redraw it. There's D. The area of D is the double integral over D of the constant function 1. Based on what we know about double integrals so far, if we're going to try to do this as a double integral, we need to maybe think of this as a vertically simple region between two graphs and use the upper curve as the upper limit of the inner integral and the lower curve as the lower limit of the inner integral. Is that possible here? Let's see how difficult it might seem here. Let's go ahead and try it. That curve's r equals cosine theta. In here, that's actually the upper curve. This curve again was r equals sine 2 theta, which by the double angle formula is 2 sine theta cos theta. If you were going to try to figure out what the limits of integration are for the inner integral to do this double integral, we'd have to write these equations in rectangular form. Find rectangular representations of these polar equations. Is that possible? I think so, but it's probably difficult. With r cos theta, you could, for example, multiply both sides by r and write that as equation as r squared equals r cos theta. And then replace r squared with x squared plus y squared and replace r cos theta with x. See what I'm doing there? taking the starting polar equation and trying to convert it to rectangular, doing a little trick, multiplying both sides by r first. That is the same as x squared plus y squared. This is the same as x. And then if I'm going to write that as a function of x, I need to solve for y. So it looks like that upper curve, this one here, is y equals square root of x minus x squared as a function of x. And the lower curve, I have to use this equation, maybe multiply both sides by r. Or, that's trickier. Multiply both sides by r squared. Could write it as r cubed equals 2r sine theta, r cos theta. I just multiply both sides by r squared. And that means I could write that as x squared plus y squared to the 3 halves. Oh, yuck. Equals 2xy. I don't think I want to do that. Okay, it sounds bad. I'd want to try to solve that for y. I don't think I want to try. Okay. If I was going to do the double integral in the ordinary way, I have to do that. That would be my lower limit of integration for the upper integral, for the inner integral. And this would be my upper limit of integration for the inner integral in the double integral. Hard. Is it easier in polar coordinates? And what do I mean by polar coordinates? In polar coordinates, when you're doing double integrals, for double integrals, instead of using dA equals dx dy or dy dx, you use dA equals what? dr d theta? d theta dr? No, neither of those. You make a slight modification. You do it as r dr d theta. Why? So here you have a general polar curve. R is a function of theta. It's wobbling as theta varies. R is going up and down. It's wobbling rotationally, you might say. The distance to the origin keeps going up and down. We're trying to find the area swept out, which would be related to the double integral of 1, and ultimately trying to find dA. And what you imagine is slicing the region up into thin slices of pizza, effectively, really thin slices, of tiny infinitesimally small angle d theta. Pretend this is an infinitesimally small angle d theta. Now it's labeled delta theta in the book, but we could label it d theta instead. And pretend it's an infinitesimally small angle. The area elements, the shaded area there, you could call dA, are, that's effectively really close to being a rectangle. Really close to being base times height. It's a sideways, curved, almost rectangle. What's the base? Say that's the base, and what's the height? The base is effectively the arc length of this little piece of the circle of radius r. They don't label it r here, but pretend this is an r instead of an r1. That radius times the radian measure of the angle does give you the arc length of that little line segment. Why? Think about it here. What's the circumference of a circle of radius r? 2 pi r. The angle all the way around, 2 pi times r. It's proportional. The arc length of a little tiny angle, little tiny arc of a circle, is the angle in radians times the radius. This radius r1 is r, and that angle is d theta. That length there is effectively r d theta, r times d theta, if you like. And this length right there is effectively dr, a small radial distance. That's intuitively the hand-wavy derivation of where this equation comes from. So to do the integral in polar coordinates, you combine these things and say the area is going to be the double integral over d of 1 r dr d theta. But you have to then figure out how to do that by choosing appropriate limits of integration for r and theta. We still would, even in doing this in polar coordinates, have to break this up into pieces, just like we did 10 minutes ago, 15 minutes ago. We still would have to do that because this region as a polar curve, so to speak, I mean, you could think of it as a piecewise function. You could think of it as this piece first, right here, and then this piece, which is made up of these two functions up here. We still would have to do it as a sum of two integrals. Or else, okay, we can write it as one integral. Theta goes from 0 to pi over 2. R goes from 0 out to this piecewise function. Let me give this piecewise function a name. I'll call it g of theta. rdrd theta. Where g of theta is a piecewise function, just like we talked about before, equal to this bottom piece, which is sine 2 theta, when theta is between 0 and pi over 6. I'm talking about the exact same thing I was talking about 15 minutes ago. Sine 2 theta, when theta is between 0 and pi over 6. And is the upper piece, this piece here, cosine theta, when theta is between pi over 6 and pi over 2. So the g becomes a piecewise function. In this example, it's not going to be typically piecewise in your examples. We can actually do the first step of the integral here pretty easily. Think about it here. I'm integrating r dr. That's 1/2 r squared. R goes from 0 to g of theta. Hey, that's going to give me the integral for area swept out, 1/2 times the integral from 0 to pi over 2, in this case, of g of theta squared, where g of theta, again, is this piecewise function, which, to finish it, you'd have to do in the exact same way I showed you 15 minutes ago. You'd have to write it as the sum of two integrals, because g of theta is piecewise. This would ultimately be 1/2 times the integral from 0 to pi over 6 of sine squared 2 theta plus 1/2 times the integral from pi over 6 to pi over 2 of cos squared theta. Exact same thing we did. So doing this one as a double integral is not really worthwhile because it's more work, but there's other ones where it is worthwhile. And this is illustrating that by letting dA equal rdrd theta, we ultimately end up getting 1/2 r squared there, which leads to the same formula for area swept out by a polar curve from before. But again, to finish it for this example, you'd have to use the fact that g is piecewise because of the tricky nature of this region. If we're just focused on one of these polar curves, then it's easier. But polar coordinates, this equation effectively, are useful for more than just finding areas. They're useful for finding any kind of double integral in certain situations, at least. Volumes under surfaces. In general, if we're doing a double integral of some function, which you could call f of xy to start with, over some domain, that is hopefully easy to describe in polar coordinates. The general situation, the picture might look like this. You're varying between two angles, and your region D looks like this. Theta is going from, say, alpha to beta. There's your region D. And R is going from, oh, I forget what letters the book uses. Okay, G1 and G2 it looks like. That curve right here is G1 of theta. This curve here is G2 of theta. If your region of integration, D, looks like that, or something that may not look explicitly like this kind of picture, but could be thought of that way. I'll let you know what I mean by that in a second. In this kind of situation, do this integral as follows. Replace dA with rdrd theta. Replace x and y with the conversion equations. Replace x with r cos theta and y with r sine theta. dA gets replaced with r drd theta. Theta is going to go, look at the picture, from alpha to beta. And r goes from G1 of theta to G2 of theta. That's how you do the double integral in polar coordinates. Now you might say this looks like it might be harder, but it's often easier. And sometimes this region, by the way, might be like a circle, or a half a circle, or a quarter circle, maybe because G1 is 0. Let's go ahead and do an example over a quarter circle, say. Well, or maybe a whole circle. This is section 13.3, number 3, say. Our function f of xy is 3x minus y plus 4. Our domain D is the region enclosed by a circle of radius, the unit circle, enclosed by a circle of radius 1 centered at the origin. There's D. This circle is the unit circle. Let's have Mathematica do the integral both in rectangular and polar coordinates, and we think about which one's easier to do by hand. So if we're going to do this one in rectangular, what would we have to do? So f of xy, I'll go ahead and define, is a nice simple function, a linear function. 3x minus y plus 4. If we were going to do the double integral in rectangular coordinates to find the volume under the graph of this, which would be above the xy plane, by the way, because of the adding 4. So we're going to find a volume under a surface. It'd be a plane, actually, because it's a linear function. And above the circle, that's at the bottom here, we'd let x go from -1 to 1. I'm going to do dy dx here at the end. And y go from the lower semicircle, negative square root of 1 minus x squared, to positive square root of 1 minus x squared. F of xy dy dx. That would be the integral you would do, and the volume, the answer is going to be 4 pi. 12.57 or something like that. Yeah. If you were going to do it by hand, what would happen when you do the inner integral? The inner integral would actually be easy to do. Doesn't matter that the limits of integration are complicated because you're treating those as constants. You're integrating with respect to y there. Integrating with respect to y would be easy. Plugging in those limits of integration would be easy. But then the outer integral could be difficult because you'd have to do that one. In this particular example, it wouldn't be too hard because I'm noticing a 1 minus x squared there and a linear function of x there. That still would be tricky. I mean, you could try a substitution, let u equal 1 minus x squared. D would be negative 2x dx. That would be good for this part, but not so good for the plus 4 there. Yeah, you'd have to break it into 2 integrals, and one of them would be a regular substitution, like I just mentioned, and one would be a trig substitution, effectively integrating square root of 1 minus x squared with trig substitution. I think like x equals sine theta. It's complicated. Doing it by hand without making a mistake probably take at least 15, 20 minutes. Is polar coordinates easier? Well, first of all, you got to plug in r cos theta for x and r sine theta for y, you get that. You'd have to multiply that by r before you do the inner integral and expand it. That's the inner integral function that you need to integrate with respect to r. It's not too difficult to do. Think about it. Integrating that with respect to r, treat theta as a constant. You get a 2r squared when you integrate that one. You get a r cubed cos theta when you integrate that one. And minus r cubed sine theta over 3 when you integrate that one. Inner integral would be easy. Would the outer integral be easy or hard? Theta is going around the circle. I go from 0 to 2 pi. Let's go ahead and do the double integral right away here. R is going from 0 to 1. Oh, the limits of integration are easy here. It's the unit circle. Theta is going around the horn from 0 to 2 pi, that way. R is just going from 0 to 1. The circle is a constant function of theta. R equals 1. Limits of integration are constants. It would be easy to do. After doing the inner integral with respect to r, there's the confirmation of the final answer. You would get a function of theta that is easy to integrate. Definitely easier to use polar coordinates.